Okay, hello everyone. Do you have any questions about the last times? Oh, mm, If no, maybe let us start the new topic. Originally, I wanted to tell about distal functions, but then decided that maybe it's better to tell some more rigorous things about what we already studied, namely about Legendre polynomials and about such problems in general. Uh, so the topic is called Sturm-Liouville theory. What what in this is about the operator of such form. Uh, so, about problems of such form. Uh, Maybe we can put here Fn. So, one over a W, like it stands for weight. Basically, it's a problem about diagonalization of the operator L hat equals to 1 over W of x mm, P of x. So, how to write this d in dx, d in dx, P of x, d in dx plus Q of x over W of x. So we have such a kind of differential operator. Such product means composition. And since we first act with d in dx, then multiply by P of x, and then act with another d in dx. So this is what is written there. And so this on this part can be written as P of x d in dx squared plus P prime of x d in dx. Right? Q. Yes. Yes. So, and we want to diagonalize this operator. So essentially, we are writing L times Fn equals to minus lambda n Fn. This is the eigenvalue problem. So, and are there any questions about this? So, so we still need to write some boundary conditions for this operator, but we will do it later. Maybe we can do it now. So first, we need to say that there are some conditions satisfied by these functions. So w of x should be greater than 0 for all x. P of x should be greater or equal than 0. First, okay. Okay. This problem lives on some finite interval, x from a to b. Q of x should be bounded from above. It should be less or equal as than plus infinity. Right. And now about the boundary conditions. How to say it? Wait. No, I'm missing plus and minus infinity probably. Wait. No. Sorry. It should be bounded from above, but not necessarily from below. So there are these general conditions for these functions, and I will explain a little bit later why we ask for this. And then there are some boundary conditions for this problem. So there are two options. One option is when p of x vanishes on the boundary. P of a equals to 0. When I write a, I mean that it can be either one boundary or another boundary. It can be also p of b. So if we have this, then no other conditions on f. Except the general condition that fn of a should be finite. No, it should be defined at that point. Another case is when p of a is non-zero. In this case, there are boundary conditions like f of fn of a plus we'll say include p of a here, but maybe it's not necessary. Alpha plus beta p of a and prime of a equals to 0. It is the most general boundary condition. Maybe alpha tilde. It's the most general boundary conditions, or we can consider simplified versions like fn of a equals to 0, or fn prime of a equals to 0. So there are also these options. So there is such a problem, and let us look at some simple examples. Not so simple examples as well. So, there is, of course, a trivial example when p of x equals to w of x equals to 1, and q of x equals to 0. And we have this standard problem about diagonalization of second derivative operator due to index squared fn equals to minus lambda n fn. And we also need to choose some boundary conditions. So p of x is 1, so we have to choose among these conditions. So let us also fix a equals to 1, a equals to 0, b equals to 1. So fn of 0 equals fn of a, or fn of 1 equals to 0. And what are the solutions of this problem? What are lambdas and what are corresponding fn's? But no, who is lambda n? Okay. Let us write this sine of square root of lambda n fn equals to square root of sine of lambda n x. Yeah, but does it satisfy boundary conditions or not? Uh, yes, so we can put here n pi, and then square root of lambda n equals to n pi. So lambda n equals to n squared pi squared, right? So there are some functions of these forms. There's sine. There is also a sine of 2 of 2 pi x, something like this. There is a sine of 3 pi x, something like this, and there are all these functions, and actually all the properties of solutions of Sturm-Liouville problems can be captured by this case. So I think. No, maybe it would be correct to say that whatever property you can imagine here, if it is some qualitative property of solutions, then this property will hold for a general problem. For example, we see here that the number of zeros of solution increases by 1 when we go to the next eigenvalue. We know that such functions form a complete basis. In a sense, we can use a Fourier transform to represent any reasonable function on this interval. So what else? I also know that these functions are orthogonal. So So all this holds for generic Sturm-Liouville problem. And I'm going to prove it today. But before that, let us consider another example. So it was the first example. And the second example, which we already studied, but without solving this equation explicitly, are these Legendre polynomials. So originally it was what? It was this equation, 1 over sine of theta, d in d theta, uh, sine of theta, d p l m in d theta, minus m squared over sine squared of theta, p l m equals to minus l plus 1 p l m. Okay. We know that these L's are actually integers, but this is something that we can check. So at least we know some solutions of this equation for integer L's, but we still need to show that there are no other solutions. And so who can tell what are the values of P, Q, and W in this case? So P of theta. Mm-hmm. And mm-hmm. Thanks. Mm-hmm. Thanks. And by the way, what is the interval AB? Well, minus pi is too much because our coordinate goes from this spherical angle, how to call it, this theta coordinate varies from 0 to pi. It is this coordinate. So from 0 to pi. Those are, I don't know how to write it better, but condition is that this p of x should vanish only at the boundaries, so not not inside the interval. No, so it is one way to write this equation. Another way is to change the coordinate to say that we choose coordinate x, which is sine sine which is cosine of theta. So now in this case. We have what? We will have d in dx 1 minus x squared d pl m of x dx minus m squared over 1 minus x squared pl m of x equals to minus l plus 1 pl m of x. So in this case, P of theta will be 1 minus x squared. Q of P of x, sorry. Q of x will be minus m squared over 1 minus x squared, and w of theta, w of x, what will it be? Thanks. And here there is the case when P of x vanishes at the boundaries. So 1 and minus 1 corresponds to cosine of theta equals to 0 or to pi. It means that we don't have any conditions on the eigenfunction of this operators, except that they are regular. And we see that these Legendre polynomials actually don't vanish. The boundaries, they are simply some polynomials. And you also see that these functions which appear in this problem are not invariants. In a sense, we can change coordinate and get some other functions. You can compute this transformation in the general case. And, we will use this formulation. So, and let us try to see what precisely happens with Legendre polynomials. So it is clear how to solve this problem. In a sense, we can simply solve this equation such that one boundary condition is already satisfied, and we want to satisfy another boundary condition. But in this case, it is a little bit more complicated. But let us try simply to solve this equation. Let us consider the case m equals to 0 for simplicity. So we have this equation 1 minus x squared d to f in dx squared minus 2x df in dx equals to minus L plus 1. So, and the most naive idea which works is to say that our f is some series in X. So in principle, we could write this series around x equals to minus 1, but since there is some symmetry x to minus x, it is easier to write a series around 0. So we write that f is some sum of cns times x to the nth power. And let us substitute this into our equation. So the first term was 1. We'll give sum from n equals to 0 to infinity cn n minus 1 x to n minus 2 minus almost the same expression Cn n minus 1 x to the n. This expression, then minus sum from n to 0 to infinity to Cn n x to the n plus so we have such a sum, and we notice here that powers of x are a little bit different. So we would like to shift summation index in the first term to have some equation on these coefficients. And if we do this, then we'll have actually we can write this sum from n equals to 2, because the first two terms for n equals to 0 and n equals to 1 simply vanish. So we can write this as a sum of from n equals to 0 to infinity, and we write overall x to the n, and compute this coefficient. So it will be n plus 2, n plus 1, yes, minus n minus 1, this c n plus 2, and then c n or simply write sum of all coefficients, and this is minus n minus 1 minus 2n plus l times l plus 1. And this, and all this equals to 0. So all the coefficients of the series should vanish, because this should vanish as a function. It gives some relation on Cns. So it gives some ratio of Cn plus 2 over Cn. So who can tell the precise expression for this? But we can simplify it already, because this is n squared minus n, then plus 2n, everything with minus sign, because but this minus sign is removed when we go to when we move it to the right hand side, and overall it is n plus 1 minus l plus 1. Right? Yes. So we have this recurrence, and in principle we can solve it. But maybe it is better to rewrite it in the form Cn plus 2 equals Cn times this, but it doesn't matter, actually. So we see the following, that if these coefficients are all present, if none of them vanish, then this ratio goes to 1 when n goes to infinity. So it means that so it is precisely the condition that computes the radius of convergence of some series. So if Cn is not zero for arbitrary big N, then f of x has singularity at the absolute value. Oh, actually, not even at the absolute value of x equals to uh, 1, but simply at x equals to 1 and minus 1. F of 1, f of plus minus 1 equals infinity. Because this series starts and divergent when we approach 1 or infinity. So there. Hmm? But if Cn plus, well, you can simply change the coordinate to x squared, and then it will be a condition for coefficients of expansion in x squared. Because there are two independent recurrence relations for odd ends and for even ends. So we can say that this function is kind of sum of Cn even x to n plus x times sum over plus 1 to n Cn odd to n, maybe like this, and here again integers to n plus 1 x to n. So we see that this series is divergent, and so it directly contradicts our condition that should be imposed in this case. This function goes to infinity, and it is the analog of condition that that our function should vanish on the other boundary in case when p is non-zero. So our only option to resolve this problem is to say that one of these coefficients should vanish. So therefore, there should exist some number n star such that Cn plus 2, Cn star plus 2 vanishes. And star plus 2 equals to 0. So it is some integer number. And if you look at this enumerator, so it's positive integer number. If you look at this numerator, then we clearly see that one root of it is L, another root is -1 minus L, but we don't care because it is negative. So uh, uh, so this n star equals to L. And since it is integer, then we see that L should also be integer. So in this case, our polynomial is our function. F of x is C L x to the L plus C L minus 2 x to L minus 2 plus and so on, and plus the last term, whatever it is, x or constant, depending on parity of L. And we know that these solutions for integer L's are Legendre polynomials. So it does not directly follow from such formulas for their coefficients. So although, of course, we can solve this recurrence relation, write exact formulas for CNs and identify them with, for example, Lie-Robrig's formula with Legendre polynomials. But here we can simply say that we already know that there are such solutions of this equation. So there are these polynomials, and this is kind of explanation why they should be polynomials. So, are there any questions about this? If you try to draw a picture like that, then what? There is this interval from -1 to 1. So P0 is 1, P1 is x, P2 is 3 over 2x squared minus 1/2. So it vanishes x plus minus 1 over square root of 3. And there's constant. And so what is its value in boundary cell? So its values are 1. So let me draw it correctly. So like this. And so we see the same phenomenon concerning zeros of these solutions. The first solution does not have 0 in this interval. The first solution has a single 0 at 0. Second solution has 2 zeros in this interval. So it wasn't obvious from the original problem, but it will follow from the general theory. So if you draw a third polynomial, then I don't know precisely what are its values at the 1 and -1, but its zeros will be located like this. 1 0 is at 0 because it is odd, and the other two zeros will be here and here. In a sense, mm, uh, zeros of two consecutive polynomials, it should be cubic. So are located in between of each other. So. Hmm? Hmm? Mm-hmm. Because if it appears, then we will see precisely this problem. We fix n is integer, so n equals to L. So there is no chance for n that differs from 1 to vanish this numerator. So this numerator will be always non-vanishing, and we will have this divergent series in powers of x of different parity. So that part of series should simply be 0. Because if it's non-zero, then it does not terminate and produces the singularity at the boundary. The part, oh, but you asked precisely about this, right? So if it does not equal to 0, then it produces infinitely many CNs which are also non-zero. Because you cannot ask at the same time that n star plus that this equation vanishes, and at the same time n minus 1 times n minus L plus 1 also vanish. So you cannot have this at the same time. Because if you subtract them, then it simply tells that n equals to 0. Right? Yes. But all other ends are defined by this recurrence relation. If one of them vanishes, then all other CNs also vanish. Yes, because they're given by Cn star plus 2 times some non-vanishing coefficient. But it does not matter anymore because Cn star plus 2 was already 0. So Cn plus Cn star plus 2 was equal to Cn star times n star plus 1 minus L plus 1 over n star. So and Cn star plus 4 equals to C star plus 2 times well, the same shifted by 1. So this equals to 0. So this equals to 0. This equals to 0. Once some of them vanish, then all other coefficients also vanish. So in this way, we actually proved that there are no other solutions of that equation. So only Legendre polynomials. Okay, so now let's go to some general theory. So the first statement is that such operator is symmetric with respect to a scalar product with weight W of x. With respect to the scalar product, this is defined as scalar product of f with g is integral from a to b dx w of x f of x g of x. And symmetric means that L acting on F multiplied by G is the same as F scalar product with L times G. So let us prove this. Let us simply compute the scalar product L times F with G. I will integrate everything by parts. It is kind of a hint. So the integral from a to b. I can immediately cancel this w with the weight in the integration measure, and it will be integral in dx g of x in d in dx d in dx f of p of x and df in dx. This plus g of x, f of x, q of x. Now let's integrate by parts. So you see that this term is the same for both expressions for the scalar product of LF with G and vice versa. But this looks a little bit non-symmetric. So let us integrate it by parts to make it a bit more symmetric. It will be the integral from. So first we need to write the boundary terms. So it will be g of x, p of x, df in dx from a to b plus integral in dx from a to b. And here it is minus g of minus dg in dx, p of x, and df in dx. one term and another term. So, mm, so now it is symmetric. And if we want to compare it with expression when g is exchanged with f, we can simply write the same integral plus a different boundary term when g is exchanged with f. So it will be f of x, p of x, dg in dx from a to b, plus the same integral. So we need the equality of these two terms. Let us write it maybe on this blackboard. So this should be compared at two boundaries, A and B. And now we see how everything works on these boundary conditions. So if P of A is 0 or at some boundary, then the storm simply vanishes there, because it is multiplied by P of X. Now, if it does not vanish. By the way, I forgot to write that there is also a third possibility here. We can identify ends of this interval a problem on a circle. So we can ask that f of a equals to f of b, and fn and fn of fn prime of a equals to fn prime of b. And this is also the option here. So if these two functions simply coincide at a and b, and all these functions in our equation should also be periodic. So at least p should be periodic, but maybe it's better to ask all of them to be periodic. Q of x equals to q of a equals to q of b, but maybe this one is not necessary. And this one is necessary at least because we have derivative of Phys, so it should be continuous. Probably we can erase on this condition. Hmm? Hmm. No, but it can be discontinuous. It can be one at uh, hmm? So, and it's perfectly fine. For example, quantum mechanical problems can be considered for discontinuous potentials, and actually there are the main two examples. So it's not a problem to have discontinuities in Q or in W, so only F, only P should be continuous. Mm. But its derivative should not be continuous already, I think. Yes, it should not be. Yes, so there are this simple examples when these terms vanish because of they either coincide or some of them vanish. But in this case, we need to compute something. Uh, so uh, in the case 2. And we need to write that so it is P of A, G of A, F prime of A, minus G of F prime of A minus G of minus F of A, G prime of A, plus maybe it was minus sign, plus the same for B. So let us substitute this condition. So F prime is alpha over this expression is alpha over alpha tilde minus alpha over alpha tilde G of A F of A. Where? Which one? This? Because it is the over a limit. So, and on the other boundary, it is G satisfies the same condition. So it is alpha over alpha tilde G of A F of A G of A plus the same as B. So it vanishes. Right? So the questions about this. So and there is yeah, yes. So we proved on this already. Yes, our operators act on the space of functions with these boundary conditions. So it acts on its domain. So these functions should have should satisfy these boundary conditions, and they should be twice differentiable, because otherwise we cannot act. So it is the domain of the operator L, and Actually, this way we define transpose operator, and to say that it is not only symmetric but self-adjoint, we should say that the space of functions on which L is defined and transposed operator is defined are the same, but here it is true. Maybe I don't want to go into these details. I can simply write that domain of L is a domain of L transposed. Maybe no. Maybe I can show an example when it is not true. So let us consider this example. To do this, we also need to introduce complex conjugation, because here everything was real and we could avoid this. But in general situation, it should be not a transpose operator, but a Hermitian conjugate. So this L is self-adjoint. Well, this operator is minus I d in dx, which I can call P. That's a mental operator in quantum mechanics. We can also define how is it called, semi-bilinear scalar product by the integral from a to b f conjugated of x times g of x, and we want to compute the difference of p f with g minus f p g. So this will be the integral from a to b I f bar prime times g plus f bar g prime dx. So it is I f bar prime of a and g of a plus f bar of a g of a oh, sorry, what, no, sorry, what am I writing? Just simply f bar of a g of a minus f bar of b g of b. So and here one function is in the domain, so this function is in the domain of operator P. This function is in the domain of operator P Hermitian conjugate. So it's simply a space of functions on which these operators are defined. And we need to make some choice about these domains, so they will be connected. So we want this operator to be symmetric. So we can choose a domain of P as functions that vanish on at both boundaries. So option 1 is a domain of P is fixed to be functions f of a equals to f of b equals to 0. But if we choose this, if those functions vanish on both boundaries, then there are no additional constraints on g. So g of a and g of b can be arbitrary. G of a g of b so this is a domain of conjugate operator. Domain of P of P dagger. So we took two little functions in the domain of P. So domain of conjugate operator is too big, and they don't coincide. Now, so we can try another option. We can ask functions in domain of P to vanish only on one boundary. Something f of a equals to 0, and don't touch the other boundary. F such f of a equals to 0. But in this case we will have this other term which should vanish. So we should take a domain of P omega equal to such functions that vanish on the other boundary. G of b equals to 0. So it does not coincide with the domain of P. And well, we can consider other possibilities, but well, just one possibility. It's clear that they still don't coincide. And here, the only option to make this operator actually self-adjoint is to consider periodic boundary conditions. So if you close this circle, then it will be self-adjoint. So. Yes, because so in the so it's some small upgrade of this naive finite dimensional formula that you should be able to move operator between different multiples in the scalar product. We should also say that they act on the same space, operator and its conjugate. So, and physically, this means this self-adjointness versus not self-adjointness means that a system is either closed or non-closed. So this momentum operator is an operator that shifts a particle with a constant speed. So if you choose it as a Hamiltonian, it will induce evolution, which is simply motion with a constant velocity. And if we put a particle on such interval, then it will escape in finite time, and probability will not be conserved. But if it lives on a circle, then probability is conserved, and this is precisely what self-adjointness means. Yes, because here we see that we have both f uh, and f and f prime in this condition. For example, if you consider the case when f equals f on the boundary equals to 0 for simplicity, then this condition, this term vanish, but this term will not vanish because it is df in dx, which is non-zero, and it will require that a g on this boundary should vanish. So and vice versa. So on the other boundary is the same. So and we can do the same analysis for generic boundary conditions. It will be the same. So if you ask something for f, then it requires the same condition for g. So. And we actually saw an example of the first derivative operator, which was self-adjoint. It was a d in d5 operator. This minus I d in d5 operator on a circle, it had eigenvalues equal to m. It was precisely in that case. So, are there any questions? And the point is that properties of self-adjoint operators essentially repeat properties of symmetric matrices in the real case or Hermitian matrices in the complex case. For example, the eigenvalues will be real. The eigenvectors corresponding to different eigenvalues will be orthogonal. And I am going to prove it now. So probably let us erase this example about Legendre polynomials. Oh, why is it so? Because actually, when I wrote the scalar product, it was defined on the real functions, but I can simply put here over a line. If the functions are real, then it does not change anything. But maybe it is better to work with Hermitian product from the very beginning. So suppose that some fn satisfies the an eigenvector condition. L acting on Fn equals to lambda n Fn minus lambda n Fn. Let us consider its scalar product with Fn. Because, well, it doesn't matter. Because operators in quantum mechanics always have heads, so I put it automatically. So let us compute its scalar product with Fn. So yes, so on one side it equals to wait, it looks too simple. On one side it equals to lambda n Fn times Fn. On the other side, it equals to L acting on Fn. So we can move it to the first place in this scalar product. And because it is symmetric and Hermitian, since it was real originally. And here it equals to the scalar product of lambda n Fn with F minus lambda n Fn with Fn. So it equals to, or what does it equal to? Oh, but it is lambda n conjugate because I modified the scalar product. So to minus lambda n bar. Fn is Fn. So and Fn scalar product Fn with Fn is greater or equal than 0, so it's definitely non-zero. So lambda n equals to lambda n bar. So are there any questions? They are like eigenvalues of a Hermitian matrix. Yes, yes. This choice of sign is because if you consider simply a second derivative operator, then its eigenvalues are negative. It's minus y squared and n squared. And in quantum mechanics, there's even more radical solution. People simply put minus sign overall. Maybe I should have done the same here, but it will increase the number of minus signs, I think. So, so people usually write minus I pi squared, but I don't want to do this. So now another property which is also analogous to a property of Hermitian matrices. orthogonal complement to the eigenfunction, so which is the space of such functions g, such that scalar product of f with g equals to 0, is an invariant under the action of L. Well, let me write like this. So in a sense, L acting on if an orthogonal complement is inside this orthogonal complement. So, and let us prove this. So we simply take some function g in the orthogonal complement, and try to compute the scalar product with f. Scalar product of the action of L on G. So in the next step, we can immediately move L to the first position. It will be L, F, G. And then we use the fact that it is the eigenvalue of L. So it is minus lambda n F G. But G is in the orthogonal complement, so it is 0. Therefore, lambda G L acting on G is in the orthogonal complement. So is it okay? So what else? Now there is another property. I don't know. Shall we erase the definitions or not? No, maybe let us keep the definition. Let me erase this blackboard. So another property is more related to this second derivative operator, to properties of differential equations. This properties says that the spectrum of L is simple. So one eigenfunction for one eigenvalue, one Fn for one lambda n. And we can ask such questions about number of Fns because we have some second order equation. Namely, we would expect two solutions, but now we will see what the problems with the second solution are. I suppose that we have f and g, which are eigenfunctions of L. In a sense, we have both equations, like n equals to minus lambda n, fn L gn equals to minus lambda n gn. So we suppose that this holds at the same time. And let us consider the following object. So there is a so-called Wronskian of the two functions. And it is defined as follows. It is fn prime gn minus gn prime fn. It's in definition. And let us compute the following object. Let us compute x derivative of p of x Wronskian of fn and gn. So this is d in dx p of x. And let me write only the first term, and then add the second term by symmetry. Dfn in dx gn minus at the same term with fn and gn exchanged. So, so there is one term when everything acts on p of x dfn in dx. So it is d in dx p of x dfn in dx times gn. And then there is a term when this derivative acts on the second function plus p of x dfn in dx dgn in dx. Minus exchanged. So what happens with this term when we subtract analogous expression with exchanged fn and gn? Yes. And actually it is also the case for the first term, because let us look at the definition of this eigenvalue property. So we can write that this derivative d in dx of well, let me just write on this on the new line. So it equals to minus lambda n w of x minus w of x at times fn times gn. maybe let us write like this, plus q of x fn. Everything is multiplied by gn, right? So the equation is here. So this operator acts on f and gives minus lambda times f. So this second order operator, so if you act only with the second order operator, we will have lambda n multiplied by w minus the other term. So on the point is that we obtain something that does not contain derivative and is simply proportional to fn. Right? And then we need to subtract the exchange expression. The same expression was fn exchanged with gn. So what do we get as a result? Thanks. So it means that Wronskian of the two solutions multiplied by p of x is a constant. Times p of x is constant. Yes, but why? Yes, it's true. Because if p of bound p of a is 0 and this constant is non-zero, then it means that this Wronskian of f and g has singularity at the boundary. And this is precisely a singularity of that kind which we obtained for Legendre polynomials. In a sense, we have one solution that which is nice, which is a polynomial, but another solution, the second solution of this equation, will have singularities, and it can actually be obtained from this condition about Wronskian. It is some first-order equation, and it can be solved. And if a boundary condition is of this kind, we can simply compute Wronskian at some boundary and see that it is 0. For example, if this boundary condition when fn and gn are both 0 at the boundary, then Wronskian vanishes because either this factor is 0 or this factor is 0. The same for the first derivatives, and it also holds for this arbitrary boundary condition. So we can simply check it. So if this is satisfied, then this constant is 0. But if this constant is 0, then fn prime gn minus gn prime fn prime gn minus gn prime fn equals to 0. So f prime n over fn equals to g prime n over gn. So it's an ODE for f, for example, and ODE for g, and it can be easily solved. It simply says that f equals c times g. Inside the interval. Yeah. So maybe I should write here something like for x is in a b, and if x is in the open interval, it should be strictly greater than 0 for x in the open interval. Because putting p of x equals to 0 is more or less putting some boundary at this point. So it's the end point of the interval. So if we put p of x equals to 0 somewhere in between, it will separate our problem into two non-interacting pieces. So we will have two different spectral problems on different intervals, and eigenvalues. So it will be something strange actually. So we will have eigenfunctions which are one eigenfunction is 0 and 1 interval, another eigenfunction is something on the other interval, and vice versa. So we will have a kind of union of spectra of these two problems, and this is possible because if you try to act with such an operator on a discontinuous function, then discontinuity of the first derivative, which appears when we act with d in dx, will be killed by multiplication by p of x. And then d in dx will produce another discontinuous function, but it will still be a normal function without delta functions. So this operator will be able to act on functions that have jump in the first derivative at zeros of p. So that's why setting p of x equals to 0 at some points will effectively separate our interval into several pieces. So on the we allow it to be 0 only at the boundaries. So here we obtain that f is proportional to g, so it's the same eigenfunction up to the overall factor. So now maybe let me first prove the most essential property of this Sturm-Liouville operator, and then we'll talk about details the next time. So the most essential property is that because well, we can open a textbook and solve this ODE, but we can do a shortcut saying that this is a linear ODE on F. So it has a no, fn prime over fn is something. Some function, gen prime over gen is in the same function. What is specifically the question? So what is written here is that d log of fn minus log of gn equals to 0. So yes. So well, there are also some properties of these eigenfunctions and eigenvalues, and the main property is that this lambda n's should go to infinity when n goes to infinity. Oh, we saw it in this examples about the interval, about Legendre polynomials. And we see that actually in both examples they behave the same way. Uh, they go to infinity quadratically, and the point is that it is their behavior in a generic case that will prove it the next time. The main idea is that when we consider quickly oscillating solutions, then all of them look like this science. So there is a lot of solutions of this eigenvalue problem for very big values of lambda that behave essentially like science with huge number of zeros. So this equation has infinitely many eigenvalues, and then go to infinity. So we'll prove it the next time. But this time, I want to prove that all these eigenfunctions form a complete basis. Actually, to be honest, we had to prove that such eigenfunctions exist, and we'll also do it next time. But here, let us simply use use them to to define an analog of for a series for such such an operator. By the way, this operator is called Sturm-Liouville operator. Probably I didn't write it, but it is this, and this is called Sturm-Liouville problem. So. Well, the statement means that we can write any function, some, let us call it f of x, or maybe phi of x is a sum from n equals to 0 to infinity, Cn fn of x. and so which practically means that so this infinite sum should be defined somehow, and convergence should also be defined somehow. So the statement is that a limit when n goes to infinity of the norm of the norm f of x, so phi of x minus sum of Cn fn of x equals to 0. And these coefficients in the expansion are defined precisely as in the Fourier transform. As scalar products normalized by norms. As L2 convergence. Yes. And we know that so, but if this function is continuous, then L2 convergence will imply pointwise convergence, maybe even the uniform convergence. And if it is discontinuous, we already saw this example with the Fourier transform, that there is a Gibbs phenomenon that two functions converge in L2 norm. They also converge pointwise if you fix some point. But if you check their difference for all possible points, then there are always some excess values when the value of partial sum is different from the value of original function by some finite number, which does not go to 0. Yes, two scalar products of Fn with phi. But actually, the time is almost over, or just over, and it's kind of a new topic. So maybe let us continue this tomorrow. Maybe I can maybe let me show some kind of sketch of this proof and then continue tomorrow. So the idea of this proof is the following. We denote this difference by delta phi n, and we compute the following object: delta phi n L delta phi n. Since this operation removes all eigenvalues that are less than lambda n, this scalar product will be less or equal, it will be greater or equal than lambda n acting on scalar product of delta phi n with delta phi n. So the scalar product of delta phi with delta phi is less or equal than okay, probably I should have put here minus sine minus L. Yes. So delta phi n is less or equal than 1 over lambda n, and here and this equals to phi L phi, because minus phi L phi. Plus these terms that come from difference. Think. Oh, actually, it will be with minus sign. Something like lambda n cn maybe norms of offense. So we'll compute it more explicitly next time. But idea is that this term does not depend on n. This term for positive lambdas only decreases the result. So we can write that this scalar product is less or equal than 1 over lambda n times. So, for example, if we make all lambdas positive by shifting up the separator by some constant, it will be 1 over lambda n times phi L phi. And since lambda goes to infinity, it goes to 0 when n goes to infinity. And so this also goes to 0. And hmm? This or hmm? Oh yes, thank you. So well, actually, to do this, we need first to shift all eigenvalues. We need to shift the separator such that all its eigenvalues are positive. Otherwise, we will need to take care about negative eigenvalues. But if we will prove that if there are some requirements of on Q, like this one, then lambdas are bounded from below, and we can shift it by constant to make all of them positive. And then this term will only decrease the answer. So it is simply because scalar product of Phys L3 equals to this sum with so phi L phi. If you suppose that it has such an expansion, is sum from n equals to 0 to infinity, fn squared Cn squared minus lambda n, because eigenvalues of L are minus lambdas. Yeah, right. Hmm? Yes, yes. So here I simply write that when we take phi and remove the part that corresponds to eigenvalues up to lambda n, then norm of not a norm, but such an object like action of L multiplied by this vector will equal to the whole thing, this one, minus the contribution from this small eigenvalues. This is what is written here. So it decreases the answer. Maybe actually it was better to put minus in the operator, but what is doing this? So, yes. Also, so this is a kind of proof up to some details. For example, we need to prove that this is actually bigger than lambda n, because intuitively it should be clear that we took some function, we took this function phi, and we subtracted all the contributions corresponding to small eigenvalues of L. So it acts on the remaining subspace only with big eigenvalues, and hmm? Yes, we are kind of. It's not like proof, but an explanation why it works. But it can be said more rigorously, and we'll do it the next time. But modulo this, the argument is precisely this: that if you have this eigenfunctions, then there is this restriction on the norm, and it goes to 0. So, okay. Are there any other questions? Okay. No, thanks for your attention. See you tomorrow.